let's get this lecture started. Hello, everybody. How you been doing? Hopefully you're all well, ready to jump back into it. Let's get things on the road. So, yeah, I was worried there for a second, didn't have a lot of people joining. I resent the link, so hopefully if anyone lost that link, they now have it. Let's just jump right back in where we were last time. Cylinders and quadric surfaces. Don't know if you like the new makeover. And we're going dark mode. Turning off the cameras just to make sure that we don't have, as little interference as possible. But I've been working so long on the computer these days that I decided to go dark mode. It's a little bit easier on the eyes. So we are going to have class in inverted colors. That being said, let's actually just jump into it. So review of last time, we spoke about cylinders and quadric surfaces. Yes, I already ordered. I'm way ahead of you, AJ. I already ordered some blue light glasses, some blocking. Yeah. So you're waiting for them to come in the mail. So last time we looked at cylinders and quadric surfaces. These are two kinds of surfaces that you needed to know how to sketch. Cylinders, what do we know about cylinders? Well, as long as they're not planes, they're not planar cylinders, we will have two variables in the equation. So if you see an equation where only two variables present and you know you're in 3D, then that thing is going to be a cylinder. So like y equals x squared or x squared plus z squared equals 1 is a cylinder. Now, if you graph that 2D sketch in the plane of the variables that are present, so for example, like for the x squared over 9 plus, to admit some people. So if you have like the x squared over 9 plus the z squared equals 1, you can sketch that. You should know that's an ellipse. That is called the generating curve. And you kind of slide that generating curve along an axis to create the 2D figure. Now, the missing variable is the guy that tells you what the axis is. So, or what it's parallel to rather. So since the y is missing from here, you know that the axis of this cylinder is parallel to the y-axis. And in fact, it is the y-axis exactly because this is centered at 0, 0. So that's how we could graph cylinders. There's an infinite variety of them generated by any generating curve that you can think of. A plane is in fact a generating curve that is, a plane is a cylinder that's generated by a line, and that kind of breaks the mold of regular cylinders in terms of the criteria I mentioned earlier. So if you only have two variables in the equation, it's a cylinder, as long as it's not a plane. And the missing variable tells you the axis that you are parallel to. Then we moved on to quadric surfaces. There were 6 types of these guys. Unlike cylinders, which you have an infinite variety, pretty much any curve you have, you can take and create a cylinder. With the quadric surfaces, these were guys that have equations like this. So these are just higher dimensional quadratics. We call them quadric surfaces. So you think of things where there's a squared power somewhere. Okay, so we had the ellipsoid, the cone, the elliptic paraboloid, the hyperboloid of 1 sheet, the hyperbolic paraboloid, the hyperboloid of 2 sheets, and so on and so forth. And we figured out how to draw those with traces. Draw several points of view, and you put those points of view together on 3D axes, and then you kind of combine them to get the entire figure that you want to talk about. That being said, we did a bunch of examples, and we sketched through some of these very slowly, and hence here we are. So that was just a quick recap of what happened last week. Now we're moving on to the next section. And by the way, we have 3 sections left in the semester. I'm definitely going to finish 1 section today, and we're going to finish about half of another section. So we'll have 1.5 sections to cover over the next week or so. So to start with some announcements, which I told the other class, so maybe I'll start there. So just to make sure that we're aware, possible dates for the final. So you don't go into super social distancing procedures on these dates. You do have to have a PC or a computer and your Blackboard up. So possible final exam dates. One possibility, Monday, May 18. And this would be from 1 to 3:15 p.m. Another possibility, Tuesday, May 19, 1 to 3:15 p.m. The other possibility is Thursday, May 21. And this one is from 3:30 to 5:45 p.m. Okay, so these are the possible dates for the final. It's going to be one of these, not all of these, obviously. So just kind of make sure that you have those times kind of blocked off on your calendar. As far as I know, none of these times should conflict with anything. Of course, you can do your due diligence to make sure of that, but these would have been time slots during which normal math finals would have been given. So you really shouldn't be having any conflicts anywhere. It's just that they haven't decided on one of these dates. So I don't know, I just know these are the ones that are in the running. So those are the possible dates. What else? Last test next week. Next Thursday. So that is going to be, let's see.
Oh, Professor?
Yeah.
Is there a possible date for the final? On top
May
you put
14th.
like...
Yes, possible dates. It's going to be one of these 3 time slots.
But I think on Tuesday, May 19th, I have another final, so at the exact like same time.
So this one, you have a conflict already?
Yeah, I have a final.
All right, so I'll make sure that they know about that then.
Mm-hmm.
All right. Okay, good. The rest of you make sure to check. You really shouldn't have any conflicts, but if you do, you need to let me know about it so I can alert the people who are setting up the schedule. Okay, so our last test is next Thursday. That's May 14th. Of course, again, I'll post a review for you guys to go through. These are the possible final exam dates. And with that, we are going to move on. We're going to talk about functions of several variables today. So usually we're used to looking at functions of a single variable calculus. So something like y equals x squared in 2D, which is a parabola, or something like x squared plus y squared equals 4 in 2D, which is a circle. So now we want to actually think about other situations, because normally how we kind of interpret it is that the y is our dependent variable and the x is our independent variable. Okay, so someone else has a conflict on Tuesday, so maybe it's something that's going to keep happening. Anyway, so normally how we think of functions, we have an x and a y. We usually imagine the world in 2D, in math class anyway, where the horizontal axis is the x, the vertical axis is the y, the x is the independent variable. So the x is doing something and the y is responding to it. The y will do something depending on what the x does. X is input, y is output. However, this, while it is very useful in many, many contexts, you would of course realize that in life, things often depend on more than one factor. So the fact that the y only depends on this one thing, it depends on the value of x, it's not realistic for a lot of situations. Sometimes you need a lot of inputs, you need a lot of factors to go into making a decision or seeing what a function is going to do. So if you want to decide, for example, how healthy you are, there are several numbers that are going to go into that, right? You go to the doctor, you get a checkup, he's going to check your blood pressure, he's going to check your blood sugar levels, he's going to check your hormone levels, your A1C, you know, what your heart rate is. There are so many numbers that will go into, is this person healthy or does this person need other things? So there are many inputs in that case. Or if you're looking at a company, and you want to be able to judge its fundamentals because you're interested in buying a lot of stock in this company or something like that, you're going to look at a lot of things, you know, like what's their debt, what's their income, or how many employees do they have, how many years have they been doing this business, how do they compare to their company. There's so many numbers. There are many things in life where it depends on more than one thing, and so functions that depend on more than one independent variables is a very important thing for us to learn how to deal with. So we are going to learn how to deal with functions of 2 and 3 variables specifically, but whatever we learn here can be extrapolated to more variables pretty easily after that. At least, not necessarily in a visual sense, but at least in a computational sense, because once you surpass a certain amount of dimensions, you can't even visualize what's going on. But according to the math, it's really like just adding one more component to your vector, right? And so the math is going to work out the same way, but we can just extend it very naturally, okay? So what we're going to do is we're going to look at functions now where we have several variables, and we're going to start with a 2-variable function, a function of 2 variables, okay? So say the variables are x and y. It's a function that assigns an ordered pair, x comma y, that are in some set. So we have a set D of ordered pairs. And the function is going to pick one of these ordered pairs and it's going to connect it to someone else in another set, right? So for each ordered pair, x comma y, it will send it to a single real number. We're looking at real value functions called f of xy, right? So here's the set D. You can kind of think of that as the domain of your function. In that set, you have little coordinates. You have these points just all around in this set, right? So each of these are their own x comma y. The function is going to take one of them, and then it's going to output some number on the z-axis, okay? So we have 2 inputs, x and a y. These would define some coordinate in the 2 space. And then there's going to be one output, which is we call the z. And so now we can talk about functions in this way. So that's kind of very natural. And you're going to find that a lot of things that we're going to talk about, they're going to feel very natural. Functions are going to work very similarly to how we kind of expect them to work out. But where the differences come in, I'll point it out to you guys. And of course, you're going to have difference in visualizations of your functions. So we already saw that y equals x squared is a parabola in 2 space, but in 3 space, it's a parabolic cylinder running along the z-axis. So there is difference in visualization, but for how the functions are going to work, they are kind of going to be the same. Now, just some definitions before we move on. These might come in handy later, especially considering what the final exam might look like. So just some definitions I want you guys to know about, and I'll talk about them here. So a region is just a set of points in space, okay? So a set D in R2, it's called a region. And an interior point of this region is any point that you can take that you can create a disk around that point, and it will completely be contained in that region. So whenever you can do that, you say the point that's at the center of that disk is an interior point. It's on the interior of this region. You know, a point is on the border, right? It's on the boundary of a region. If no matter what size you draw a disk around it, you will get points that are outside of the region and inside the region at the same time. Now, when a region contains all of its boundary points, we call the region a closed region. If a region only consists of interior points, we call it an open region. And of course, you can be in between. You can be neither open or closed, and so on and so forth. So these are just some things here. The open disk, where we're not including the boundary, is an example of an open region. X squared plus y squared strictly less than 1. Anywhere that is x squared plus y squared equals to 1 is on the boundary, because if you draw a disk around that, you will catch points both inside and outside the circle. If you take the disk and you include the boundary, you get a closed region. Okay, so those are just some things that you want to know about. We also need to know about bounded and unbounded. Bounded just means, intuitively, it means the region doesn't extend forever in any one direction. How you can know that this does not happen, or it does happen, is using circles centered at the origin. So pretty much take a circle centered at the origin. And then you check, are there points in my region that are outside the circle? If the answer is yes, you try to draw a bigger circle, and so on and so forth. If no matter what size circle you draw, there will always be points outside of your circle, we call the region an unbounded region. So an unbounded region means the entire region cannot fit inside a circle of finite radius around the origin. A bounded region, though, it is possible to create a circle big enough that it will encapsulate the entire region. Okay, so once I can fit my entire region inside some circle, it doesn't matter how large the radius has to be, but as long as there's a radius where I can fit everything inside, we call it a bounded region. And there are many theorems that deal with unbounded and closed and open and all that stuff. We're not really going to cover, but you kind of should know about these definitions, just in case they want to throw like a multiple choice question on you where in the final where they ask you about these definitions. So those are just some things to know. We're not actually going to do a lot of work with them. What we're going to do at this point is we're going to deal with functions. We're going to evaluate functions. We're going to plug them in. We're going to find domains and ranges and all these things. And it's going to work in many ways, in ways you'd expect, but it will also have its differences. So let's actually jump to those. So let's actually do the first one. Okay. So because it's very intuitive, we're just going to jump right into examples here. Let me know what you think is the domain of this function. Z equals the ln of x squared plus y squared. What do you think? Right, you need x squared plus y squared greater than or equal to 0 because the logarithm works the same way you'd expect it to work. What you're plugging inside the logarithm has to be positive. Log of 0 is undefined, and log of a negative is undefined when you're talking about real variable, real valued functions. Okay, so log of a negative would be a complex number. We need x squared plus y squared to be strictly greater than 0. This means that x comma y cannot be 0, 0 itself. Now, any other point is going to be fine because the moment my x or my y is not 0, the square is going to turn it into a positive number and it's going to be larger than 0. So we would say then the domain of this function of z is going to be equal to the set of all x comma y such that x comma y is not the origin. Okay, so here is already a main difference, right? So we're normally we're used to seeing intervals for domain. It's not an interval. So interval is something that lives on the real line, but here, this is actually describing a two-dimensional set of points, right? So it's like I'm in the XY plane, and this is where my domain space is. Everything is allowed except the origin itself. But other than that, at any other point, I can plug in at any other point other than the origin, I can plug in any point in this region and they're all fine, except 0, 0. So there's a two-dimensional space here that I can think of as the domain of this function. It's going to work for all coordinates in x, y, except the origin itself. So that's the difference with domain that we'll notice. It's not going to be an interval usually. Usually you'll want to describe it as a set where you talk about how the coordinates have to behave on for them to work. So here's another example. What is the domain of this one? X greater than 2? Why you say X greater than 2? Y greater than 2? Right, Y is not equal to 2 is one of them. So you need Y not equal to 2 for denominator. Anything else? Yes, so also we need the x plus y squared minus 2 to be greater than 0 for the radical. In other words, this is like me saying your x must be greater than 2 minus y squared. So I can say here, the domain of f of xy is the set of all coordinates such that your y is not 2 and your x coordinate must be greater than 2 minus the y, 2 minus y squared. Okay, so now you might wonder what that would look like. So let's see. So here you're in the xy plane. You know you cannot have y equals 2. So it's this is y equals 2. Can't touch that line. What else do we have? X must be greater than 2 minus y squared. So x is 2 minus y squared. So it starts at 2. And if for x to be 0, your y would have to be radical 2. So it's going to do below that. So this here is at square root of 2. Okay. And now you want your x to be greater than this value. Okay. So for example, so this would mean our domain would be everywhere out here, not including the red line. Okay, so that's how we can look at domains. Again, it's just a set of all values. What is f of 2 comma 3? So and this is kind of how you think. You're just gonna take the function, and everywhere you see x, you plug in a 2. Everywhere you see y, you plug in a 3. Gives you 3 as the answer. And you can talk about what is f of, it says 1 comma 2. Well, that one is undefined. Because y equals 2 is not in the domain. Okay. So again, pretty obvious stuff in terms of how functions work. They'll work the same way. Slight difference here is your domain usually isn't going to be an interval. It's going to be some region in 2 space because you have 2 variables. So there's some sort of two-dimensional space that's going to be your domain. So you can write it in set notation, and that can cover it. Here's another one. Domain and range of this function. What's domain? You can't have negative infinity to infinity. That's an interval. It's a two-variable function. It's very strange for the domain to be an interval. And even if you said it's an interval, you'd have to say on which variable. So the domain here, now this is a polynomial, and polynomials work as you would expect. You can plug in anything, right? So this will be the set of all coordinates where your x can be any real number and your y can be any real number, right? So it's not the same as saying negative infinity to infinity because that's a single interval. You could say, or you could say something like this. Your x is an element of negative infinity to infinity. That's on the real x line. And your y is an element of negative infinity to infinity. That's the way you could say it, but it'll be a pair of intervals that you'd have to compare. You can't actually just say one interval. What about the range? Yes, you could also say x, y, and r. X comma y in r. Or you could say, another way to say this is, yeah, x comma y is an element of R2. Yeah, but none of these things, none of these descriptions are intervals. What about the range of our function? What are the possible outputs? It's 1 plus x squared plus y squared. Well, I mean, well, greater than or equal to 1. So here, of course, x squared plus y squared is greater than or equal to 0. So this would mean that x squared plus y squared plus 1 is greater than or equal to 1. And we only have one output, so, or a 1D output. So an interval can actually work here. So for your range, an interval still works. It can be any z value that is equal to 1 or larger. That's going to be your range. And your domain is this guy. All right. So nothing too crazy so far. Yeah. All right, let's keep going. Of course, when we start talking about functions, we're often going to want to talk about their graphs. Well, the graph of a function of two variables is actually a surface, right? So the graph is going to be 2D And the idea is you take some x comma y coordinate in your domain, you plug it in, and it's going to boom, and it's going to output some particular z coordinate. And you can do that for all the points here in the domain. They'll all map up to different points up here. They'll all map up to different heights, right? So by plugging in any coordinate here, you'll get for each coordinate a z value. So hovering over each point, there's another point at some level, which is indicated by the output of your function. So you end up creating a two-dimensional figure here. And that ends up being the graph of a two-variable function. So the graph of a two-variable function is going to be two-dimensional. It also stands to reason, of course, a graph of a three-variable function is going to be three-dimensional, and etc. Okay, so let's see, because this is actually going to go back to the last class. So let's see who's paying attention. What would the graph of this guy look like? Okay, so this is f of xy equals the square root of x squared plus y squared. What does that graph look like? The graph of that function. It's a cone, and it's not a whole cone. It's the top half of the cone. How do we know? Well, that just means z is equal to the square root of x squared plus y squared. Now, if that doesn't look familiar, that just means if you z squared is equal to x squared plus y squared, right? But we know here z is positive. Okay, so z squared equals x squared plus y squared. That is the equation of a cone. In fact, that's the one equation of a cone that I told you that you have to remember. That's the one where it's slanted at pi over 4. So that is a conic section for you, and it's in fact okay, that guy. But of course, it goes on forever. I'm just drawing one part of it. Right? And of course, we know that the angle here is pi over 4. Okay, so that's the graph of this thing. It's a cone. It's another way to write a cone. So if I say f of x comma y is the square root of x squared plus y squared, well, that's just a cone. What about this guy? And again, we can replace this with z. What is that? Anyone? It's a plane. How we know? Well, I can bring everyone to the other side. And that's in the form of a plane. That's something we would have learned from 2 sections ago. So that's actually a plane with normal vector 2, 6, 1. And it passes through all points where that relationship 2x plus 6y plus z equals 6. Now remember how to graph a plane. Just plug in 2 variables equals 0 at a time. So for example, I plug in y and z equals 0, I would get x equals 3. If I plug in x and z equals 0, I would get y equals 1. And if I plug in, say, x and y equals 0, I would get z equals 6. So that's the plane. Now you play connect the dots. That's your plane. So yeah, so the graphs of your two variable functions, these guys that have x and a y being plugged into the function, these guys are just surfaces. And a lot of times the graphs, especially in a classroom setting, these are going to be surfaces that you already know how to sketch. So planes or some sort of cylinder or some sort of quadric surface or something like that. So whenever you're graphing these guys, it's going to be one of the guys that I already taught you how to graph under normal circumstances. So that's another thing. So domain and range work the way you would expect. You can still only plug in positive things inside a logarithm. You cannot divide by 0. Under a radical, you have to be greater than or equal to 0. All that stuff still holds true. Difference is your domain is not an interval anymore. It's now a set of coordinates. It's a two-dimensional thing. Your range you can still write as an interval because that's, again, still measuring one thing. It's only measuring something on the z-axis. So you can represent all possibles as intervals that will work for the range. The graphs, these will be 2D surfaces, and they could be any of the kinds of surfaces that I already taught you how to sketch. So yeah, there we go. Now let's talk about level curves. Very nice thing to use level curves. They actually give us a way to understand what's going on in a higher dimension by looking at a lower dimension. So how do we do level curves? So here I have some random surface in blue. What you can imagine we do is we just take a plane that's parallel to the XY plane, slicing through this thing. And then whatever the curve looks like, we project it down into 2 space. And then we draw an outline of what we can see here. Okay. Now the projection, this picture down here, these are called the level curves. So in this case, you'll just get a bunch of concentric circles. Okay. Now these technically they would start steep, and then they kind of get wider as time goes out, as it gets shallower. So those are called level curves. Now, of course, a lot of you, pretty much all of you, would have seen an example of level curves before. It works on like a map, like a contour map. Whenever you look at a map of some country or town or city or whatever, that is a 2D representation of a 3D thing, right? So if there's a hill or a mountain or something like that, we represent this in 2 dimensions using contour maps. And so what you can have is either by colors or by numbers, we can indicate the elevation of certain things. So we can have, you know, red just means it's very steep, and then blue is just means you're at one level down, and then we can have something like orange. Let's do orange. Let's do orange. Does that actually work? Did that actually work? Oh, whatever. But you guys get the idea. So things like that, contour maps, very useful. Really, we're seeing a 2D representation of something that's in 3D. And we can look at this 2D representation and kind of figure out what is actually going on in 3 space. So for example, we can talk about the level curves of this guy, which is the cone that we drew earlier. Now, mathematically speaking, what the level curves is, what it means to actually slice through with a plane, you'll notice the plane will have an equation like z equals a constant, right? So it's really when your function, you set it equal to a constant, and then you sketch whatever curve results from that. That is called a level curve. So here we can have this guy, And we can just set z equal to a constant. So if z equals 0, we would get like this point here. And if, say, z equals 1, we would get, say, this here. And we can say z equals 2. Boom. Boom. And we'd get this here. Now, all of these I can trace down. And create for us some level curves. So we can move down and talk about the level curves of this guy, level curves. And you'll have a blue, and you'll have a green, and you'll have a red. And so we can get that kind of idea. So this would be what the level curves would look like. And for a cone, there'd be very evenly spaced. That's one way you can recognize that something is a cone. There is, I guess, let's do another one. So if I had, for example, f of x, y equals x squared plus y squared, then this would be z is equal to x squared plus y squared. We recognize that as a paraboloid. So it's like a bulgy thing going up. And again, we can do a bunch of slices here. And that would lead to the level curves. This one will be different in the sense that they would start farther apart, but then they get closer as you go out farther. Right? So this here, evenly spaced, indicate steady slope. And you go down to something like here, circles get closer together as you move out, indicating we're getting steeper. Right. So you could look at the level curves. You can look at this, which is just a bunch of concentric circles, and you can look at this, which is also a bunch of concentric circles. But you'd be able to recognize this one as a cone and that one as something else, because here we get to new levels in a much quicker time space. And so here we're getting steeper as time goes on, whereas here we're just kind of staying level. So we can talk a lot about how some 3D figure looks by looking at its level curve, right? Now, we're going to talk about quote unquote level curves for functions of more variables. But as you can imagine, Here, if we're looking at something that's living in 3D space, its level curves are going to be living in 2D space. So that could stand, you can probably from this surmise, well, a function that has 3 inputs, it's going to be a 3-dimensional figure. Its level curves would have to be in 2-dimensional objects, which means its level curves are really going to become level surfaces and so on. But we'll get to that in a little bit. So let's see here. Again, I do a little thing here, but you can pretty much jump right in here. It's very natural. What is the domain of this guy? So again, just wanted you to see an example with like 3 variables, f of x, y, z, right? Now, again, we need y minus x to be greater than 0 for the ln. And we need z to not be 0 for the fraction. And so here, the domain of f is going to be the set of all 3 coordinates, or set of all triples, such that y is greater than x and your z is not 0. So you have to be on the, from this perspective, it would be to the left of the plane, y equals x, from the way we draw the things, and it has to not include the xy plane. Now, Malak, you had a question? No? Did you raise your hand by accident? Okay, so that's domain. Okay, nothing new there. We're gonna moving on. How about sketching these guys? Now, I want you to be aware, and here's where, so for 3 variable functions, here's one thing I want you to notice. Can't sketch them. Right? Because they live in 4D. Okay? So you would need a whole other variable. You would need something like w equals some function of x comma y comma z. So our domain lives in 3 space. Yes, you'd get a 4D graph. So our domain would be 3 space, and then it's outputting something in another dimension somewhere where we can't even visualize what that would look like. So we can't sketch it because it would live in 4D. However, their level curves well, they become level surfaces. And they would live in 2D, live in 3D. So when you're looking at a function of 2 variables, the level curves are 2-dimensional, 1-dimensional objects that live in 2-dimensional space. So once you go up a variable, function of 3 variables, the level curves would become level surfaces. These would be 2-dimensional objects living in 3-dimensional space, and so on and so forth. So it also stands to reason that if we go to 4 variables, now even the level curves we won't be able to visualize on a 4-variable function, because that guy is going to live in 5 dimensions. His level surfaces are going to be hypersurfaces in 4 dimensions, which we can't even visualize. So, right. So we quickly outgrow being able to sketch things here with anything that has more than a handful of variables, or anything that has more than 3 variables, actually. So, but we can sketch there, we can sketch the level surfaces. Which can give us info about the function. Same way that us looking at a contour map can give us information about the landscape that we're about to walk over. So again, level surfaces for this one. So you're going to set f of x, y, z equals a constant. So this would mean that your x squared plus y squared minus z squared equals a constant. Or you could say something like z squared is equal to x squared plus y squared plus the constant. And what would that mean? So we know that if k equals 0, then that's just a cone opening in both directions. If we have k equals 1, that's a cone shifted up at level 1. We can have k equals -1, and that's a cone shifted down to -1. So what would the level surfaces look like here? It would kind of look like, concentric isn't quite the word, but because I can't really draw it specifically here, it will kind of be like concentric cones. Right, so you have a cone stacked inside of a cone, stacked inside of a cone. For every K, you get another cone that either moves up a level or down a level. And of course, this continues towards the bottom. So you have a cone here inside of a cone, inside of a cone. And it keeps going down. So that's what the level surfaces would look like. And what you can think of this, you see how it's like when you have a two-variable function. So it's some two-dimensional thing living in 3 space. When you slice it and you do a projection, you can kind of just think of this as like a shadow of the thing being projected down into 2 space. So what you can notice this thing is you can think of the level surfaces as kind of like the shadow of a 4D figure. So your shadow is just always is going to be a dimension below you. Okay, so you're 3-dimensional, you're going to cast a 2-dimensional shadow. If you're 4-dimensional, you're going to cast a 3-dimensional shadow. So these concentric cones here, they're like the shadow of whatever this thing is that lives in 4D. I have no idea what it's going to look like, but hey, its shadow is 3-dimensional and it looks like a bunch of concentric cones. So that's just a little mind equals blown moment there, sure. You can do this for another thing. And again, this is another thing where conceptually it's something that you know. I don't think you'd ever be tested to actually sketch a bunch of level curves, but I would want you to have the ability to be able to take something and match it to pictures of the level curve. Because something like the final that you would be getting, I would assume something like that's going to pop up. You'll see things like that in your homework and your textbook as well. So if you are given a function and they give you a bunch of pictures and they say, match this function with a picture of its level curves, I want you to kind of know how to actually do that. Or not kind of, I want you to know how to actually do that. So again, here we have level surfaces. So we're going to set f of x, y, z equals k, which means that x squared plus z squared minus y equals k, which means I can solve for my y And sketching a couple of these, if your k equals 0, that's just y equals x squared plus z squared. We know that that is a paraboloid opening along the y. And if we have like k equals 1, that is a paraboloid opening along the y, but it starts at 1. Or we have k equals -1. That is a paraboloid opening along the y, but it starts at -1. And so the level surfaces, if someone were to draw a picture of this, while it's not 100% accurate, you should kind of have the notion that this would be the right picture. Into like a concentric paraboloids going all the way down. And of course, it goes all the way back there. And there are, of course, bigger ones going here, going all the way back. But yeah, you would, if you see a picture like that, that's the picture you would match with this thing. Okay. So that's kind of all we want you to know about functions at this point. Domain, range, kind of how you expect. The difference is you might not have intervals, you might have sets that you want to describe, but your functions work the same way they do. So whenever things should be positive, it's still going to be the same. If you can't divide by 0, you still can't divide by 0. Can't have negative under an even radical, things of that sort. The graphs of functions of 2 variables are actually surfaces like cones and cylinders and quadric surfaces that I told you about. The graph of 3-dimensional functions are 3-dimensional objects. 3 variable functions, these are 3D objects that live in 3 space. Okay, the graph, then we looked at the graphs, well, whatever I should say. The graph of 3 variable functions will live in 4 space, right? So there'll be 3D objects in 4 space and so on. But their level curves is something that can be useful in studying some object, especially if you don't want to work in as high a dimension. You can kind of look like a shadow of the thing and kind of talk about the thing itself. Not going to do much about that, but the thing that I would expect them to ask you about here is like matching pictures, right? So if someone put this picture and put that picture and put like this equation, you should know that the second picture goes with that equation, the level surfaces. That's basically it. So very kind of fuzzy, but I think the things that you will need to be able to do computationally in this section will be very natural for you to do because the functions are going to work very similarly. So just really want to talk about this and talk about the nuances. And other than that, we're actually just going to move on to limits and continuity in higher dimensions. So this is something else we're going to talk about. We're not going to talk about the full section today. We'll get through about half of it. So another thing where we're going to skip a lot of the background concepts. Oh, yes, question. No. Yeah, so another thing that we're going to skip a lot of the background concepts. Hopefully you remember about limits from Calc 1. A lot of concepts were explained there. Hopefully you remember them all. If not, go back and watch the Calc 1 videos. So intuitively, let's talk about limits in the single variable context, right? So you have y equals f of x, and you talk about the limit as x approaches a of f of x, and you say it equals L. What are you trying to say? Okay, so when we say the limit as x approaches a of f of x equals L, what it means is as the x values get close to a, the y values will get close to L. So the limit was a way to track the outputs of a function once you actually manipulate the inputs of the function, okay? So as your inputs get close to this thing, your outputs will get close to the other thing. Another thing that we used in single variable calculus is that sometimes we had to look at limits from one side at a time, right? So there was the left side and there was the right side, right? So we had a one-sided limits where sometimes to figure out what a function is doing, we have to look at, well, what is it doing on this side? What is it doing on that side? And do they match up? So if the one-side limits gave you the same value, you know, oh, you just define that to be the value of the limit, because that's what happens to the y value. If you're in a situation where one side gives you one value and the other side gives you another value, that means the limit does not exist, because you can't say what the output is when your input is getting to something, because there's a different answers here. So it introduces ambiguity that we don't like. Okay, so all those concepts I expect you to know. Moving on to 3D, it's very similar. So intuitively, we have this huge limit here. So you'll see that the notation got a lot more beefy. So here we're tracking two variables, x comma y, as it approaches a comma b, right? Of a two variable function, f of x, y equals L. Well, what does that mean? Okay, well, it means as the coordinate x, y approaches a, b, then the output f of x, y is going to approach the value L. Now remember, f of x, y is going to be the output in the z axis. Okay, now there is a precise definition. You might have remembered the epsilon delta definition from Calc 1. There is a corresponding epsilon delta definition for these guys as well. So this is it here. Now we're not going to use this epsilon delta definition much, but you should know it. I would say you'd want to have that memorized because again, while we're not going to test your ability to use it, if someone's writing a final where they're giving like multiple choice or short answer, which I think your final is going to look like, this is something that they could easily just ask you about. Okay. Now I'm going to talk about what that means here and even how to look at the precise definition a little bit, but we're not going to go into it in detail. We're going to just kind of skip it and deal with a more intuitive definition. So what does this mean? What does it mean for x comma y to get close to a comma b? Well, it means that if your a comma b is the center of some circle, x comma y we say gets close to it if it gets within that circle. So now the radius of the circle is delta. So this is the circle where the equation is x minus a squared plus y minus b squared equals delta squared. And of course, you can actually square root both sides, and that's where that expression is coming from. So the square root of x minus a squared plus y minus b squared less than delta, it's coming from you imagining that there's a disk that's around this coordinate. And we consider it close when once our coordinates, so here x comma y, not close, right? Whereas this x comma y is close. So close is defined whether or not you're within this circle. And once your coordinates get within that circle, we're saying that the output would be get very close to L. How close? Within epsilon close. So once your points get inside the circle of radius delta, that's close to a comma b, your outputs would get very close to the number L. It'll be L plus or minus a little bit, and that little bit is called delta epsilon. Okay, that's the backwards E. Okay, so another view here. So I have points x comma y. These are my x comma y's. They're in the xy plane. As they inch close to this, you'll notice that my z values are inching closer and closer to the L value. And so we can say the limit as x comma y approaches a comma b, you will get an answer close to L. Okay, so that's kind of the intuitive definition. Now, some differences. what can cause a limit to not exist is something that we want to discuss first. And that's going to be the last thing that we discuss today. So the rest of the class is just going to be talking about when a limit can break in this higher dimension. So remember how we can define a limit to break in a lower dimension. There were one-sided limits. If the left and the right don't agree, then the limit does not exist, okay? In higher dimensions, this idea has to be like taken on steroids. Okay, so because when you talk about directions in 3 space, like what we have here, there is no left and right anymore. You can approach the point A, B from a bunch of different places. So I can come in from this direction here, boom, hit the point A, B. But I can also come in at a curve, boom, hit the point A, B. I can come in at this curve, boom, hit the point A, B. I can come along a spiral, boom. I can come along a straight line, boom, right? So there are multiple ways to approach the point AB. There are multiple ways to get close to AB. And how many ways are there to get close to AB? Well, as you would probably have guessed, there's an infinite number of ways. So once we're in higher dimensions, we don't have to keep our eyes on 2 directions. We have to keep our eyes on all directions, an infinite number of directions, right? Because there are so many ways that we can get close to the point AB that there's an infinite number of ways. Like there's like whatever path someone approaches this point in, you can find a different way to get close to that point. Okay, so that's where the differences would come in, and that is also the idea that we're going to use to show that a limit does not exist. Okay, so showing that a limit does not exist, it's going to be easier than showing that a limit does exist. So we're going to talk about that first. Okay, what I put in the box here, these are the steps, and we're going to go through these steps, and we're going to do a bunch of examples. We're going to do all these examples here. Okay, so boom. Okay, we're going to start with this one. Okay, now showing a limit does not exist comparatively is easier. Oftentimes what you'll see a problem that says specifically, show that this limit does not exist. And the idea that you're going to take to show this is, you're going to show that I can approach the point from different paths and get a different answer. Okay, that's the goal. So how do you go about achieving this goal? Now, we will need to know how to prove that limit does exist, but that's for next lecture. That's a whole other ballgame. Okay, right now I just want to focus on showing that it does not exist. So all we have to do is show that 2 of these paths don't agree. Like if I approach get close from this angle versus that angle, this would give me a different answer from that. That tells me that the limit will not exist. Okay, how do we know what paths to approach and how to actually set this up? So here are the steps, right? Just 3 steps, 3 basic ideas. The first is to choose the obvious path that passes through the point AB, right? So if you have a coordinate A, comma B, A and B are constants, then one obvious path is choose x equals A. This would be a vertical line running through A, and it's obvious, it's easy. X equals a constant, gets the job done, you get to the path. Another obvious path would be y equals B, right? This would be a horizontal line that passes through the coordinate A, comma B, right? These are kind of the more obvious things to choose because the numbers are right there in front of you, okay? So you can run along these paths. So let's say you have an example where it's going to A, comma B. You can approach along x equals A, see what answer you get. Approach along y equals B, see if you get a different answer. If you get a different answer, then boom, you're done. The limit does not exist. However, step 2 tells you, step 2 right here, is don't be redundant, right? So if you kind of notice that they're going to give you the same answer, which in a lot of cases, it would be obvious that they would give you the same answer, just ignore the other one. Your goal is to show that you get different answers by coming from 2 different paths. So if you're getting the same answer, it's actually not going to help you at all. So Don't be redundant. So if you're gonna get the same answer, don't even bother. Okay, now there are less obvious paths that you would try. So you go along obvious paths, you get one answer. How can you figure out whether there is another answer out there? You would go along little less obvious paths. These paths are paths that would allow you to simplify the result, combine terms, etc. Right? Normally, and a lot of times, I wouldn't say normally, a lot of times when you do this, it will allow you to get another answer. So let me actually jump into this, do the first example for you, show you the ropes, kind of show you how it would go, what I'm thinking when I'm writing stuff down, and then you guys are going to do all the other examples, the other 4 examples. Okay, let's go. So here, don't want red. Here's a limit. Show that it does not exist. Okay, so I have x comma y approaches 0 comma 0 of xy over x squared plus y squared. All right, so what I'm going to do is I'm going to approach along an obvious path, along x equals 0. What is my limit going to be, right? So I'm calling the limit L. Well, this would be the limit as 0 comma y, because remember my x is 0, is approaching 0 comma 0. But what does that mean? Well, there's 0 over 0 squared plus y squared. That is just the limit of 0 over y squared. And the y is getting close to 0. That is 0. Okay? So I'm like, all right. Now I move down and I realize that along y equals 0 would give the same answer. So skip. I'm not going to waste my time. Notice that I have xy in the numerator. If I plug in my y equals 0, I'm obviously going to get 0. So I'm not going to be redundant. That's just a waste of my time. So what I'm going to do now is I want to pick something that's going to allow me to combine terms. Does anyone see some of that, a path that goes through the origin that would allow me to combine terms, like some equation? So not like x equals 0, something else. Another path I can go along. Two? What do you mean 2? X equals 2? So this, not valid. You cannot do that. Do you see why? The path must go through the point, right? So x equals 2 does not pass through 0 comma 0. I must be able to approach the point, right? So if I'm on the 0 comma 0 is over here, x equal 2 is a line over here, right? It's never going to pass through the point. I could pick x equals 0 because that actually works. So here, if I have my axes, here is 0 comma 0. X equals 0 is the y-axis. That's like me approaching from this point right here or along there, right? So that's definitely passing through the point. I need to pick something that passes through the point. So here's one. What about along x equals y? Now that definitely passes through the origin, right? If I look at x equals y, so that's like here, I have my origin 0 comma 0. X equals y is like coming along a straight line at a 45-degree angle, right? So that would definitely work. Along x equals y, what does my limit look like? Well, it's going to be the limit of, well, I can just plug in x comma x because my y would be x. And I'm just going to plug in y equals x everywhere because they're the same. So in the top, I would have x times x. In the bottom, I would have x squared plus x squared. Now what's going to happen? You'll see that the top is x squared. The bottom, I have 2x squares. I can combine the terms. This allows me to simplify the x squares. And what's the answer now? So now I pretty much have the limit of a half, which is a half. Now a half is cool and all, but there's a problem. It happens to not be equal to 0, which was the answer I got before. So notice that when I went along x equals 0, the limit gives me 0, right? So the z value heads to 0. However, if I approach the same point along a different path, along x equals y, the limit now gives me a half, which means the z value is now approaching a half. Well, it can't approach 0 and a half at the same time. Therefore, the limit does not exist. Okay? And that's how you would show that a limit does not exist. Choose 2 paths that give you a different answer. One, the obvious path. Choose x equals a constant or y equals a constant that passes through the point. 2, a path that allows you to combine terms. Choosing x equals y allows me to get an x squared plus an x squared in the denominator. I can combine those into 2x squares. That allows me to cancel stuff and get another number. So that's a good path. Of course, be careful. You can't just run along anything you want to plug in numbers to get something different. That is not allowed. You have to approach the point. Your x comma y must approach 0 comma 0, which means you need to pick a path that will actually pass through the coordinate that you care about. So in this example, I could not pick x equals 2. I could not pick something like y equals x plus 1. These guys were not valid because they do not pass through 0 comma 0. But other than that, I can pick any curve under the sun, anything. I could have approached through y equals x squared. I could have approached through y equals x cubed over 7. I could approach like anything, right? Anything that would give me a 0 that would pass through 0 comma 0 is valid. Now, the moment I can pass through 2 different paths, get a different answer, limit does not exist. Okay. Hopefully we got that. All right, you guys are going to do these now. Guess I can keep moving these down. Okay. All right, go. Your turn. Okay, thanks Ash for volunteering. Limit as x comma y approaches 0 comma 0 of x y squared all over x squared plus y to the 4th. Ideas, right? So along x equals 0, it's a fine choice. Along x equals 0, what's going to happen? Well, our limit is going to look like 0 comma y approaches 0. And of course, you'll notice that after writing down the limit once, I kind of get lazy and just write LIM after that. It's understood that I'm taking the same limit, but it gets kind of annoying to rewrite that all the time. So this is one of the 2 times in this class you're allowed to be sloppy. So one time was when we were talking about limits of sequences because it's always n approaches infinity. So you don't have to write n approaches infinity, you can just write LIM. This is another time. Once you tell me what limit you're approaching once in a higher dimension, you don't need to tell me again because it's really annoying. So plug in x equals 0, I would get 0 over 0 squared plus y to the 4th. And of course, that gives me 0. All right. So it approaches 0. Yes, x equals 0, very respectable choice as AJ points out. Another, x equals y to the 9th. Okay, that's interesting. X equals y to the 9th. So oh, x equals y squared. How do you mistype the 9 for a square? It's like on the other side of the keyboard. Okay, because I'm like, that's a very interesting guess. Oh, you got the 3 by 3? Okay. Yeah, I still feel like the 2 and the 9 are far away from the 3 by 3 because they're still far away. Okay, yeah. So I don't know. Y to the 9th is a very strange thing to pick. Let's go with x equals y squared. Right now, hopefully you all see why he. Hopefully you see why that would make sense. Like if I replace all x's with y squared, then I go here and I plug in y squared for the x, plug in another y squared for this x, plug in, and that's the y to the 4th. Now, what that allows him to do is get a y 4th in the place of the x term in the bottom, right? So that's y to the 4th now, plus y to the 4th, and on top you have y to the 4th. So that again would actually simplify to a half because you have 2y to the 4th in the bottom. And yeah, that gives you a half here, which is not 0, which we had before. So limit does not exist. It is what it is. I feel like that's a meme. Okay. All right. So yeah. All right. AJ, you're up since you were bullying Ash. What do you want to do with this one? So limit as x comma y approaches 1 comma 0 of y over x plus y minus 1. I don't know why you'd call that a God path because x equals y doesn't always work. In fact, x equals y would not work in this case. So the line x equals y would not pass through 1 comma 0. Now, Ash is jumping in with y equals x plus 1. I think you would mean x equals y plus 1. That would work. However, again, don't forget the steps. Don't forget your training, grasshoppers. Follow the steps. That will ensure you won't have to work harder than you have to. Step 1, what is the first thing you want to try? The obvious paths, right? So, yes, as you would suggest, I would pass through x equals 1. That makes a lot of sense. It's an obvious path. X equals 1, it passes through 1 comma 0. What would the limit look like? Well, it would look like the limit of it would look like the limit of 1 comma y approaches 1 comma 0 of y over x, which is 1 plus y minus 1. That would simplify to 1. Right, that just gives you y over y. All right, another path. Y equals 0. It's another obvious path. Do we ever do two obvious paths at once? Well, yeah, if it's not redundant. If I plug in y equals 0, this is like x comma 0 moving towards 1, 0. So it's like the x, so I fix the y to be 0 and my x is inching closer and closer to 1. So plug in 0 for y. And that just looks like, well, 0 over x minus 1. And that limit is 0, which is not 1. Limit does not exist. All right, cool. What about this one? Oh, you think that limit was sneaky? Okay. All right, x equals 0. Makes sense. Obvious path, right? Our limit would look like the limit 0 comma y approaches 0, 0. So this is just the limit, and essentially it's y approaching 0 of sine squared y over y squared. What is that limit? It is not 0. This is a special trig limit, not infinity. Limit as theta approaches 0 of sine theta over theta. No, we didn't need the squeeze theorem here. I mean, you can prove it with the squeeze theorem, but you should know it's 1. You could also prove it with L'Hopital's rule if you wanted to. But the limit is 1. It's a special trig limit. You should know that. So here, this limit is 1 squared. So it's actually 1. Give me another path. Someone wants the God path, x equals y. X equals sine of y. So I see what you're looking for here. This x equals sine y is going to allow you to combine the top, but what would you do with the denominator? Because now you're going to create 2 sine squared y plus y in the denominator, plus a y squared. Again, I would go with an obvious path. You guys are thinking too hard. You guys don't realize that y equals 0 is actually going to give us a different answer. So this would be x squared plus sine of 0 is 0 over 2x squared plus 0. So that's a half, which is not 1 last time I checked. Half is not equal to 1. Limit does not exist. Don't forget your training, grasshoppers, okay? Not only do we have to get the right answer, we have to get it with style. We have to not work too hard. We have to look like we're not trying. Okay, go to the obvious paths first. The only time you don't check both obvious paths is if you realize that they're going to give you the same thing. I can see right away here, plug in both x and y equals 0 would give me the same thing. That's why I skipped it. But you'll notice in this example, I approached both obvious paths. X goes through 1, y goes through 0. They gave me different answers. Same thing here. Approaching the obvious paths get the job done. I didn't need anything too fancy. Of course, it can do one more for extra practice. Do this one. So we learned a lot of things. What about this one? Because Ash wants more practice. I totally with him on the more practice thing. All right, let's practice on this one. X equals 0. Excellent choice. Along x equals 0, the limit would look like, well, the limit 0 over 0 plus y squared. That's going to give you 0. Okay, cool. Another path? Okay, I mean, there's a y in the numerator, so that's going to look very similar. I mean, it'll also give you 0. X equals y, the God path, as a wise man once said. Okay, let's try x equals y. So I'm going to go in, I'm going to replace all y's with x's. What would we have? So the top would give us x cubed, and the bottom would give us 2x squared. So this cancels that, and we are left with the limit of x over 2 as x is approaching 0. Nope, that's also 0, guys. God path didn't work. Other ideas? You know what? Sometimes actually approaching at a slope can change things. So this is a strategy that you can try sometimes. Sometimes this works. So not along x equals y, but along x equals, say, ky, a constant times y. Your limit would look like say ky is everywhere. So this is going to be k squared y cubed over k squared y squared plus y squared. Yes. Then, is this going to give us something else? Well, this is a k squared y cubed. In the bottom, I can factor out a y squared. I would get k squared plus 1. This cancels that. Nope, 0 again. Jeez. Last time, x equals y squared. Is that going to work? Our L is going to be the limit x equals y squared. This has to work. Okay, that would be y to the 4th times y. That's y to the 5th. This would be y to the 4th plus y squared. Is this going to do anything? Y to the 5th over, can factor out a y squared. I get y squared. I get y squared plus 1. Then cancel that. I would have the limit of y cubed over y squared plus 1 as y is approaching 0, and that gives me 0. Yo, bro. Why Jhevon like put this sentence there? Like, I feel Jhevon's like trying to trick us, bro. Yo, you think the limit is actually 0? Yes, it is. Shark. So you come upon a guy like this, you are going to spend a long time trying to figure out how to get a different answer, and you're not going to get one. Now, this also showcases another important reason that you'd want to follow the strategy that I mentioned here. Because otherwise, if you're just keep going and trying random paths, you're never going to know when to stop. Another reason to follow the strategy. Once you try, now, I won't say this is something that's true in general, but in a Calculus 2 class or a Calculus 3 class, the problems that you're going to see, this is statistically speaking going to happen very often. Once you actually try those two kinds of paths that I mentioned to you, like a path that is an obvious path and another path that allows you to simplify or combine terms, and you kind of try to not be redundant. Once you kind of follow those strategies, then if after 2 or 3 times you can't get a different answer, chances are it's a fake out. It's going to be another one. So there are times when, as I mentioned, they'll specifically state in a problem, show that the limit does not exist. However, there are other times when they're going to say something like, determine whether the limit exists or not and prove your claim, right? Now, when you don't know of existence or not, you want to be able to get to a decision very quickly. You want to be able to know, okay, yeah, I know for sure this doesn't exist. Or, I think this might exist. Let me try to prove that it exists. So following the strategy is going to get you to one of these decisions very quickly. And I would say, if you're not sure whether you should be proving that it exists or not, I would probably try to show that it does not exist first. Because again, usually, especially with a lot of experience, within 2 tries, you'll know whether that's true, right? You pick the obvious path and you pick another path that allows you to simplify things a convenient way. And you would be able to spot these 2 paths relatively quickly after you do a lot of these things. So you should actually try that first. Now, if you go through a bunch of these paths and you realize you're getting the same answer, then maybe that's actually the answer, you know? So I read a little joke yesterday. Like the other class, they started getting suspicious that I was going to try to trick them, but they got suspicious on the problem before this one. And then I had to talk them in, no, you guys can trust me. I'm not going to do that to you, blah, blah, blah. And then I hit them with this, was the funniest thing. I laughed a little bit too hard. Yeah. So. Yeah, I saw some people noticing in the comments, but I don't know. Ash was like, maybe in the end the limit does exist. This one does exist. As for how to show that it exists, that's next time. Now, by the time we get to the exam, you're going to be an expert on this. Don't worry about it. It's going to be fine. Whether it exists or not, you will be able to identify it and you'll be able to pull it off, right? Because we're not going to use the epsilon delta definition. We're going to use something that allows us to show that the epsilon delta definition is going to work, even though you're not going through it. It's actually using the squeeze theorem. So we're going to use this theorem to prove it next time. It is something that you need to know how to do, so we're gonna do that. But for now, have your basic conceptual understanding of a limit and know how to prove a limit does not exist, and you go to this strategy is the go-to strategy. So hopefully that answers it. So you have the 3 possible final exam dates up. I see a lot of conflicts on Tuesday, but hopefully we can figure something out. I'm going to make sure that they know that. Okay, you also have a conflict on Thursday. Okay, so we're going to figure something out, but we'll stop there. And yeah, so you have the 3 possible dates. So for all of you, try to make sure that you don't have any conflicts on those dates. Last test is next Thursday, so you'll post a review for that. I'll post a review for that later in the week. What else? Nothing else at this point. I don't really have any new information other than that at this point. It's just those 2 things. So we'll stop there. Like I said, I'm actually filling in for another class.
When are you gonna get the grade for the exam?
Oh, the grade for these? I don't know. After next week. It's not going to be this week, for sure. So, and oh, as for Brittany, I wrote that in the beginning of class, what the dates are. So you'll see it in the notes. So that was on the previous page. So there they are right here. All right, take care, everybody. I'm filling in for another 212 class. So I'm going to run to the next class now. Run all the way to the other side of my desk. Feel like I'm doing something. I will catch up with you guys on Thursday. We will stop there. So we are about 1.5 sections to wrap everything up. Pretty excited. We're going to start partial derivatives next time. It's going to be pretty cool. And I'll see you guys in the next one. So take care. Bye. Yes, fresh cut. It's was done at home. Yeah. So my OneNote isn't the only thing that had a makeover. But anyway, see you guys next time. Yeah. Natalie trying to get her brownie points again. I was gonna make a joke about it, but I don't know. Okay. All right. Ciao. Have to run to the next class.